The ocean's surface is still as a flat mirror, the sun reflecting off the water in glimmering patches. Beneath the waves, an enormous shadow glides silently through the depths. More than just a vessel, this is a nuclear submarine, a leviathan of technology weighing in at around 10,000 tons. It exists in a world where traditional submarines must surface every few days to recharge their batteries, but this one remains submerged for months, completely self-sufficient. As the massive hull moves through the profound darkness of the ocean, one wonders, how does a machine of such size manage to stay submerged, never needing to break the surface to recharge? This leads us to a curious question: why do nuclear submarines never surface to recharge their batteries? Astonishingly, the answer lies in the core of their engineering, a marvel of modern science that produces the energy needed to operate these colossal machines without resurfacing for weeks or even months on end. By the end of this exploration, we'll uncover the engineering secrets that allow these submarines to defy conventional expectations, staying submerged while producing a continuous supply of power. At the heart of a nuclear submarine's abilities is its pressurized water reactor, a system that generates thermal energy via nuclear fission. This reactor creates steam that drives turbines, producing electricity on a massive scale. To grasp how remarkable this is, consider that a typical nuclear submarine, such as the Virginia class, generates a staggering 25 megawatts of electrical power from its reactor. Comparatively, a conventional diesel-electric submarine must surface every few days to run its engines and recharge its batteries, which can only store a limited amount of energy. In contrast, a nuclear submarine can operate submerged for over 90 days without surfacing, thanks primarily to its reactor. Let us delve into this mechanism step by step. The pressurized water reactor has two primary cooling loops: the primary loop, which circulates water heated by nuclear fission, and the secondary loop, which carries the steam produced from this heated water to the turbines. Imagine these loops as two separate highways, one carrying superheated water while the other transitions this heat energy into steam. This configuration allows the submarine to maintain a steady output of electricity for navigation, weaponry, and life support systems without any interruptions. To illustrate, think of a kettle scaled up to the size of a house. When you boil water in that kettle, you turn thermal energy into steam. In the submarine, the reactor continuously generates thermal energy. Engineers estimate around 150 megawatts of thermal output, through fission reactions. The primary loop functions like the heating element of the kettle, while the secondary loop directs steam to the turbines, converting that heat into mechanical energy. But what if, in our imaginative analogy, the heat was limited? Traditional submarines operate with a finite amount of energy, using batteries that can only provide power for several days before draining completely. When those batteries run low, they must return to the surface and use a diesel generator to recharge, a slow process. This is akin to a car running out of gas and needing to stop at a gas station. Nuclear submarines, however, possess an almost endless supply of fuel with their onboard reactors. Once the reactor is initialized and started, the process of nuclear fission can continue as long as there is fuel available, allowing for continuous operation without ever needing to surface for recharging. An intriguing historical example of this capability is the United States Navy's USS Nautilus, the world's first operational nuclear submarine, launched in 1954. Nautilus completed the first underwater voyage from the Pacific to the Atlantic through the North Pole without surfacing, an extraordinary feat made possible by nuclear power. Such capabilities expanded strategic military options immeasurably, enabling longer missions and more effective deterrence without the crippling need for routine resurfacing. Now, some might think, isn't it risky to remain submerged for such long periods? Yes, submerged operation poses challenges, but the engineering of nuclear submarines integrates robust safety and monitoring systems. A common misconception is that nuclear reactors are inherently unstable or dangerous. However, the designers implement comprehensive safety protocols, such as multiple redundant systems to monitor and control the reactor's temperature and pressure. The reactor core itself operates at relatively low pressure compared to other systems. It is the containment measures and cooling loops that ensure safety during operation. In terms of scale, while a conventional submarine may feel the pressure of needing to surface, a nuclear submarine operates under a different paradigm. Instead of needing to surface for energy, they function as an autonomous underwater power station. For example, the Los Angeles-class submarines can carry enough fuel to allow their reactors to operate consistently for roughly 30 years before needing to be refueled. This longevity gives them a substantial operational advantage over diesel-electric designs that depend on regular surface intervals. Reflecting on their stealthy prowess, which of these machines would you least want to be standing next to? Is it the lumbering diesel-electric submarines at the mercy of battery recharge, or the stealthy nuclear giants that continue to operate unseen? Share your thoughts below. Coming back to the workings of the nuclear reactor, it's essential to revisit a common belief. Many assume that because nuclear submarines run on nuclear energy, they must surface to vent off excess heat or exhaust. In truth, the engineering teams design these reactors to be very efficient with heat transfer. The reactor's cooling systems work tirelessly to maintain optimal temperatures without releasing much heat into the environment. The entirety of the operational infrastructure ensures that everything is kept under control, heat is reused and converted into energy, minimizing waste. Thus, while it might seem counterintuitive, the engineers engineer these systems to complete the opposite of what seems obvious. Nuclear submarines function optimally when submerged indefinitely rather than surfacing to, as one might think, vent excess heat like traditional engines do. In closing, we can take a moment to appreciate the elegance and ingenuity that conceals itself beneath the waves. Nuclear submarines represent a pinnacle of human engineering, machines that glide through the ocean depths, seemingly defying the limitations imposed on their conventional counterparts. They demonstrate how humanity has adapted and integrated complex science into mechanisms designed for survival and stealth. The nuclear reactor in a submarine is not just a power source, but a symbol of our quest for innovation and understanding of the fundamental forces that govern our world. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell me below which machine you want taken apart. Nuclear submarines are not merely powerful vessels, they are masterpieces of engineering designed to sustain their operations away from the surface for extended periods. Delving deeper into their functionality uncovers the remarkable technologies and processes that make these feats of endurance possible. A closer look at the reactor's cooling systems illustrates just how this works. The pressurized water reactor inside a nuclear submarine operates using a closed-loop system that ensures efficient heat management. The primary loop carries pressurized water that absorbs heat generated from nuclear fission. This water is heated to approximately 330 degrees Celsius while remaining under immense pressure to prevent it from boiling. This pressurized system effectively prevents any formation of steam in this loop, allowing for the efficient transfer of thermal energy. Once this hot water exits the primary loop, it moves into the secondary loop, where it passes through a heat exchanger. As the pressurized water from the primary loop transfers its heat into the secondary loop, it turns the water in the secondary loop into steam. This steam then expands and drives the turbine generators, which create the submarine's electricity. The turbines can produce significant electrical power, with the Virginia-class submarines generating roughly 25 megawatts, enough to power about 2,000 homes while remaining submerged in total silence. By cleverly designing this system, engineers have crafted a mechanism that allows for continuous power generation. Imagine a large pot simmering on the stove, the hot water remains steaming but never boiling over because it is contained. Similarly, the reactor's continuous cycle of heat transfer keeps the nuclear submarine sufficiently powered while ensuring that there is minimal loss of energy. The efficiency of this system showcases the ingenuity necessary to keep these machines on mission for long durations. But this efficiency also comes with a need for constant monitoring. The submarine's crew relies on a sophisticated array of sensors and computers that track various parameters like temperature, pressure, and radiation levels, ensuring everything remains within operational limits. This advanced monitoring system operates much like an air traffic control system for an airport, ensuring safe and efficient operations among various components of a critical environment. Historically, we can compare these systems to earlier submarines that primarily relied on batteries and diesel engines, leading to severe operational limitations. Consider the German U-boats of World War II. They could operate submerged for only limited periods, using their diesel engines on the surface for recharging. Beyond this, their operational impact was constrained by battery capacity and the need to surface regularly, vital for both mission success and crew safety. In contrast, the design and function of nuclear submarines eliminate these constraints, enabling unparalleled strategic advantages. One remarkable example heightening this contrast is the USS Seawolf, a class of submarine designed to counter advanced threats at great depths and for prolonged durations. When launched in 1993, Seawolf featured improved sonar and stealth capabilities alongside its reactor technologies. This design enables it to approach enemy tasks more adeptly, gathering intelligence without needing to rise for recharging or refueling. The operational flexibility granted by the nuclear reactor allows mission profiles that traditional submarines can only dream of, essentially converting the vast expanses of ocean into an operational space rather than a limitation. Another compelling aspect of the nuclear submarine's capabilities is how they manage oxygen levels while submerged for extended operating periods. Conventional submarines must surface periodically to replenish their oxygen supply, as they rely heavily on the physical processes of combustion. In stark contrast, nuclear submarines utilize specialized systems to produce oxygen chemically and purify the air. They often use electrolysis systems, which split water into hydrogen and oxygen, generating breathable air as a byproduct of the operations. The oxygen produced through electrolysis allows the crew to breathe comfortably while accomplishing their missions without the constant urge to surface. The membrane scrubbers used in these submarines also defeat carbon dioxide buildup, ensuring the air quality remains optimal. By continually filtering out carbon dioxide and introducing oxygen, these vessels can sustain a crew for as long as their food supplies last, often upwards of several months. This efficiency ensures that crew members can remain focused on their duties rather than concerning themselves with the constraints imposed by their living environment. For example, during an extended mission in the Arctic, the USS Connecticut managed to stay submerged for over 3 months while maintaining operational readiness and a healthy environment for the crew. It is not merely the reactor or the innovative systems that ensure survival, it's the entire integrated environment designed for efficient operation in potentially hostile conditions. Now, let's re-examine a common misconception surrounding submarine operations. Many might think that nuclear submarines inherently waste energy by remaining submerged for long periods, or that they require vast amounts of energy to sustain life on board. However, the ingenious design of modern submarines allows for operation at maximum efficiency. The systems utilize waste heat, rather than discarding it, to warm the crew quarters or even heat the water for cooking and hygiene. This closed-loop efficiency underpins everything, from keeping the reactor operational to maintaining a sustainable onboard environment. Overall, each component of a nuclear submarine, from the reactor to the environmental systems, is optimized not just for performance, but also for longevity and efficiency. This intertwining of technology and design is a core pillar of their effectiveness. As we reflect on the capabilities of these incredible machines, think about the implications they have on naval strategy and geopolitics. Countries that possess nuclear submarines project power and influence far beyond their physical borders. The ability to operate undetected anywhere in the ocean enhances deterrence against potential adversaries. The mere presence of a nuclear submarine can profoundly impact military planning and defense strategy. Furthermore, with the increasing sophistication of underwater surveillance technologies, the stealth feature granted by nuclear power is particularly compelling. A conventional submarine's dependency on surfacing regularly to recharge makes it more vulnerable to detection. In contrast, nuclear submarines excel at avoiding detection entirely, operating in silence even while the most advanced sensors are deployed. The engineering mastery behind these vessels does not just enhance their operational time, it elevates their strategic importance in an increasingly complex global landscape. Whether navigating through icy waters or stealthily patrolling coastlines, the engineering behind nuclear submarines exemplifies human ingenuity. These vessels are not merely tools, they represent a blend of advanced science and tactical foresight. The quest for continuous power generation, resilient life support, and operational stealth creates an ecosystem where technology and engineering synergize. The nuclear submarine serves as a reminder of how far we have come as a society in harnessing energy and understanding our world. These colossal machines swim through the ocean's depths, unbound by the limitations that govern so many others. The intricate balance of technology, safety, and functionality ensures that they will remain as silent sentinels beneath the waves for decades to come. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next